This is part 5 of a series on artificial neural network. In this video, we will implement an artificial neural network. This video was produced in Korean and translated into English. My voice was generated using AI, text-to-speech. In the last 4 videos, we looked at what are needed to implement a basic artificial neural network. In this video, we will implement an artificial neural network from scratch using numerical differentiation and gradient descent. Let's perform binary classification using an artificial neural network model. Let's perform linear separation with a single-layer perceptron and nonlinear separation with a multi-layer perceptron. And let's observe what happens if we use a linear activation function in the hidden layer of a multi-layer perceptron. Now let's write the code that implements a neural network. First, let's write functions that perform gradient descent using numerical differentiation. To calculate the gradient accurately, you must use automatic differentiation. However, here we use numerical differentiation to approximate the gradient. We will take a closer look at gradient descent using automatic differentiation in the error backpropagation algorithm later. Let's write a function that performs numerical differentiation. The change in loss with respect to a parameter is calculated using this formula. This is the formula we looked at in this video, and it is the center difference approximation method. H is a small change in parameter. We use this value here. X is the features of training dataset. And Y is the target value for regression or target class for classification. F-loss is a function that calculates loss. When performing binary classification, the binary cross-entropy loss will be calculated. When performing multi-class classification, the cross-entropy loss will be calculated. Additionally, when performing regression, the mean squared error loss will be calculated. Fpredict is a function that calculates y-hat, the output from a neural network. The floss and fpredict functions will be defined later. And parameters variable is the parameter list of the neural network. For example, for a 2-layered neural network, the parameter list would be as follows. WH and BH are the weights and biases of the hidden layer. And WO and BO are the weights and biases of the output layer. We read all the items in the parameter list one by one. Then calculate the gradient of the loss. Let me explain the case where I is 0. For a 2-layered neural network, P0 is WH. Find the rows and columns of the matrix WH. The matrix WH looks like this. Next, we initialize the gradient matrix. The gradient matrix looks like this. This is the set of derivatives for each element of WH at that position in the matrix WH. Initially, we set these values to all 0. Next, read the elements of matrix WH one by one. P-org is the element at this location. Increase the value of the element at this position in matrix WH by H. The values of the remaining elements are fixed. Use the change WH to calculate the y-hat, the output from the neural network. Then, use the actual y values and the predicted y-hat values to calculate the loss. This is the loss when one element in matrix WH changes by H. Next, we decrease the value of that element by h. We then calculate the changed loss using the same process as above. Now that the change in loss has been measured for a change in h, the element at that location should be restored to its original value. Next, we use this formula and the measured losses to calculate the gradient. Repeat this process for all elements of the matrix WH to complete a gradient matrix like this. Doing this for all parameters will store the gradient matrix for each parameter in the p-gradients list. Next, we write a function to perform gradient descent. Use the function defined above to perform numerical differentiation for all parameters and generate a list of gradient matrices. We then update each parameter using gradient descent and the gradient matrix. Alpha is the learning rate. The formula for gradient descent is as follows. Now, let's implement a neural network using numerical differentiation. First, let's implement a single-layered perceptron like this to perform linear binary classification. Let's use the gradient descent function we created on the previous page. The data we will use is like this. This data is organized into two clusters. The class Y of the red cluster is 0, and the class Y of the blue cluster is 1. We want to separate this data into a straight line like this. Split this data into the training and test data. Now we create a single-layered neural network model. The number of neurons in the input layer is the number of features in the training data. Here it is 2. And the number of neurons in the output layer is 1. The learning rate alpha is set to 0.1. Next, we initialize the parameters. The connection weights WO between the input layer and the output layer is a 2x1 matrix. The bias BO is a 1x1 matrix. The matrix WO is randomly initialized, and the matrix BO is initialized to 0. The parameter list contains WO and BO. Next, we write a function that calculates the value of the sigmoid activation function. Since it is a binary classification model, the output layer uses a sigmoid activation function. Then write a function to calculate the value of loss. Since it is a binary classification model, binary cross-entropy loss is used. Next, we write a function to calculate the output from this neural network. This is the prediction process. When you input data X into this neural network, the output is calculated using this formula. P0 is the matrix WO, and P1 is the matrix BO. If the proba variable is true, it returns the sigmoid value as is. Otherwise, it returns the value converted to the class. Next, we write a function that performs the training process. Repeat the following process the given number of times. Input the training data X and the validation data XVal into the current neural network and measure the loss. The parameters of the initial neural network are random values that have not yet been trained. Next, we update the parameters using mini-batch gradient descent. Create a subset of a given batch size, and perform the gradient descent on this subset. Then the parameters will be updated once. By repeating this process, the parameters are continuously updated. and the neural network is gradually trained. Now we call the train function. The number of iterations was set to 200, and the batch size was set to 50. Visually see the loss history measured during training. Then, we measure the accuracy of the training and test data. Next, we visually check the decision boundary. The following code is what we used in machine learning. Let's skip the explanation of the following code, and let's check the results. As the iteration progresses, you can see that the loss of the training and test data gradually decreases. Visualizing this, it looks like this. If you see the loss gradually decreasing, you can assume that the parameters have been updated to their optimal values. The accuracy of both the training and test data is around 0.95. The decision boundary for binary classification looks like this. Because we used a single-layer neural network, a linear decision boundary was created. If a test data point is here, we assume it is class 0 because it is to the left of the decision boundary. If a test data point is here, we assume it is class 1 because it is to the right of the decision boundary. Let's run this code. The results came out like this. Next, let's implement a two-layered perceptron. Like the previous code, we use the gradient descent function we created. The data we will use is like this. This data is organized into 3 clusters. The class Y of red cluster is 0, and the class Y of blue cluster is 1. This data is for binary classification, but it cannot be separated by a straight line. Therefore, we need to use multi-layered neural network. The decision boundary might look something like this. This nonlinear decision boundary separates red and blue data well. Let's just look at the changes to the previous code. This time we used one hidden layer with 16 neurons. Initialize the parameters WH and BH in the hidden layer. WH is a 2x16 matrix, and BH is a 1x16 matrix. And initialize the parameters WO and BO in the output layer. WO is a 16x1 matrix, and BO is a 1x1 matrix. The parameter list contains 4 matrices like this. Next, we write functions to compute the sigmoid and ReLU activation functions. The output layer uses a sigmoid activation function, and the hidden layer uses ReLU activation function. Then, write a function to calculate the binary cross-entropy loss. This step to calculate the output of the hidden layer has been added to the prediction process. The final output from the neural network can be calculated by this formula. P0 matrix WH, and P1 is the matrix BH. And P2 is the matrix WO, and P3 is the matrix BO. ReLU is used as the activation function of the hidden layer. Next, perform the training process and check the results. The following code is identical to the previous code. Let's check the results. As the iterations progress, you can see that the loss on both training and test data decreases significantly. And the decision boundary looks like this. As expected, a nonlinear decision boundary was created. If a test data point is here, we predict it is class 0 because it's outside the decision boundary. If a test data point is here, we predict it's class 1 because it is inside the decision boundary. So far, we have looked at the differences between a single-layer perceptron and a multi-layer perceptron. Let's run this code. The results are as follows. Next, let's try using a linear activation function in the hidden layer of a multi-layer perceptron and see what happens. In the previous video, we mathematically proved that even a multi-layer perceptron cannot solve nonlinear problems. If a linear activation function is used in the hidden layer. Here we will check this through an experiment. Let's remove the activation function from this step in the previous code. That is, the function f of z equals z is used in the hidden layer. The accuracy of the training and test data was lowered to 0.79. The losses decrease as iterations progress, but are higher than that of the previous code. A linear decision boundary was created, just as a single-layer neural network would have done. This model tries to separate this data into a single straight line, so the separation is not very good. Let's run this code. The results came out like this. So far, we have implemented neural networks that perform binary classification using single-layer neural network and multi-layer neural network. In the next video, we will implement a neural network that performs multi-class classification.